Mm. Yes. Okay, so today we will discuss more algorithms. Uh, so we will mostly today discuss linear regression and logistic regression. And the last class we discussed perceptron and add-line. And both of them are used for classification. Okay, be careful for classification. And today we will learn logistic regression also for classification. But we will see it's based on probability. And later on we will learn support vector machine. It is for nonlinear. If you recall perceptron and add-line, it's for linear separable data. If the data is not linear separable, you cannot use it. And later on, we will also learn tree-based. Okay. And after we learn some of the algorithms, like here it says for classification in practice, it's recommended you compare the performance of a handful of different learning algorithms, then to select the best model for your future. Okay, because if you just use one algorithm, if you don't compare, it may not do good because different algorithm may be suitable for different scenarios. It says there may be different number of features or samples, amount of noise, and data. The class is linear separable or not. So considering all of those facts, okay. And if you recall last class, when we discussed the perceptron application, we also, with sklearn, the example, we also see those steps involve training. So you select a feature based and collecting training samples. And we also choose some performance metrics. Then you need to choose a classifier. Okay, so far we haven't learned a lot, just two, perceptron and add-line. And then you evaluate, we use accuracy. So later on, we will also see how do we tune the algorithm. So sklearn, we already learned, okay, last class. And remember, for class label, you use integer. And we also do test and train data split. And we use accuracy. So all of this we already discussed. So today we will learn a new classification called logistic regression. And there is another concept called linear regression. So probably first, let's take a look. First, let's take a quick look of gradient descent. You remember last class, we learned the concept of gradient descent. Do you still remember that? Yeah, we learned gradient descent is a very important concept, okay, in machine learning. So we all need to understand that. So gradient descent, okay. So we discussed, like today we discussed regression. So we will see the linear regression, but be careful, logistic is different. So regression is to predict real value output. So what the value is. And the classification. So for regression, it's continuous, generally speaking. For classification, it's discrete. So you remember for that RS data, it's not a continuous. That it's not, it has nothing to do with each other, the samples. And the output is what? Is this Virginia or is this Sodato something, some flower? Is it? So it's not a real value. But for regression, what you want to train is you want to know what the Y value is. Is it 1.5 or 100.99 or 1,000 something? It's a value. That's the difference between these two. Be careful, okay? Okay, so you have input, is it? And so this is the training set and learning algorithm. And here, basically, the hypothesis is what? Is like the net input and with the activation function. So like the hypothesis here in this case, this is so all those points, scattered points, those are samples. Those are samples you want to know, okay, if I know this X value, can I predict what the point, where the point is going to be? Suppose if I know the X. Then in this case, you can do linear regression. So this line is the best fitted line, basically, in this case. And why we see this, it will minimize the sum of the error. So here, basically, the linear regression concept is very much like that perceptron Adeline, but the difference is perceptron Adeline is to predict what class it is. So Y is not, Y is just 1 or 0. And here the Y is a value here. You see, in this Cartesian coordinates, it's some value. Okay. And the last class, we learned the cost function. So cost function in our perceptron and the Adeline, what we choose is the sum of error. Is it the sum of the error and you square it? And over here, we also do divide by the number of samples for our linear regression, and you try to minimize it. Okay. So this is a cost function. And when we try to minimize it, we already analyze it's a quadratic function. The quadratic, so we want to find the minimum point. Minimum point is what? It's the convex lowest point. Okay, it's the bottom of the bow. And if we take a look, the cost function, so this is a cost function. And the theta 1, theta 2, or theta 0, theta 1, basically here is our W0, W1, it's the weight. So the relationship between the cost and the weight, you can see it's a bow. Is it in 3 dimensions, a bow? Okay, and you want to find the lowest point. So you find the weight, then that will give the lowest cost function. And we can also say this is the contour for that cost. And here's theta 0 and theta 1. This is in 2-dimension, not 3-dimension. It's the contour of this cost function. So gradient descent, then we can take derivative. So last class we already discussed, is it gradient? And gradually get to the lowest point. And it involves the learning rate. And when we pick the learning rate, be careful. Learning rate, if you let it too small, then it will take a long time. It will take a lot of epochs to get to the lowest point. But if it is too large, it can go overshoot. So it can miss that lowest point. So you need to do the testing training to see what's the best learning rate it's going to be. Okay. So it also involves the try. And we already discussed all of this last class. And multiple variable last class, we also showed some examples. So you can also use similar idea. So multivariate linear regression here discussed. So similar concept. And the last class, you remember we also discussed feature scaling. So feature scaling is also very important so that the gradient descent doesn't need to take a long time to converge. So you can let the gradients descent to converge fast. Feature scaling, we discussed learning rate, we discussed, and also generally speaking, your cost function. When you do the iteration, the training, the cost, just assign yourself. The cost function should decreasing. Okay, and getting approach to 0. Otherwise, it will not, otherwise that means the training is not on track. And polynomial regression. So basically you can convert this polynomial regression to linear because you can replace like the quadratic and the cubic to what? To a new, to a different feature. And then you can convert to this, so you can then still using linear regression concept. Okay, so this is general idea review about gradient descent. So linear regression here we discussed. So linear regression is you assume the output, this output and the feature has a linear relationship. And the cost function, so this is the cost function. Cost function is the sum of error 2 to the square. So this is cost function. So we can see basically this is what? This is pretty much like Adeline. Is it like Adeline? And then we can apply gradient descent. So exactly similar concept as we already learned for linear regression. So linear regression, you can also apply it to multiple features. So similar, okay. So then it calls multivariate linear regression. So anyway, it's a similar idea like you can apply gradient descent to train linear regression. So now, let's take a look. Logistic regression. So what is the concept for logistic regression? And if you recall, for the add line, this is the hypothesis. Is it for add line? The activation function is W times feature. And then it is the straight line to separate different classes. Okay, but let's think about this special scenario. So suppose you add one extra sample here. If we add one extra sample here, then you can see that separable line is going to be shifted a lot. Assuming this one extra sample is off the other samples a lot, then it will also shift the line a lot. Okay, if it's shift the line, then you will see, then the misclassification number will increase a lot. So if we use the linear activation function, that's not very efficient here for the classification. It's not a good design. So here, what the idea is, for the decision function, or we call it hypothesis function, if we change it to sigmoid function. So sigmoid function is used a lot in machine learning. If we change the hypothesis, the decision function to this format, to 1 over 1 plus e to the negative theta times x. So here, theta is our master class. All this theta is our weight. Theta is W. Okay, is master class. It's version of our W. So then just think about that one extra will shift. So it will cause more misclassified samples. But if we use sigmoid function, so this is our decision function. Okay, and this part is net input. So basically, this is sigmoid function is 1 over 1 plus. Okay, that's the format of sigmoid function. So if we use a sigmoid function, then we will see the situation completely changed. So this is that decision function. Previously, this is the decision function. Is it? So now it's changed to this. And what the line will look like? The line will look like this. And if you have this line, then regarding that case, did you see? So you will, even though you have this extreme data points added, you won't have the misclassification. Is it in this case? So here, what your classification is, if this decision function value is greater or equal than 0.5, then you classify it as 1. Otherwise, you classify it as 0. It makes much more sense in this case. Is it? So you use this decision function if its value is greater than the 0.5. And what this represents? This represents probability of a particular sample belong to the class. So it just represents possibility, probability. Okay, so if the value is somewhere here, that means the probability it will belong to class 1 is about 55%. That's what it means here. Okay, so it's based on probability here. This is about logistic regression. Then because of the logistic is on the probability, is it? So what it will be the cost function. So we cannot use sum of error, sum of the square of error. We cannot use that as our cost function. So here we have another concept called likelihood. So you want to maximize, because here is based on probability. Is it? Because of probability, you want to maximize the probability, the possibility. So the likelihood is what? Is given that weight and the feature will generate this output. The probability it will classify the sample correct or not. So based on that, you should consider what? Consider all samples probability. That's why you need to times all of the samples probability. What the probability is? The probability is either that phi or it's the probability belong to that class, or if the possibility not belong to that class. Is it? So that's why it's probability 2 to the y, or if the probability 1 minus probability 2 to the 1 minus 1. Is it? So you just times all of this together for all of the samples. So this is called the likelihood function. So for this likelihood, then we take a nature law of the likelihood. This is a cost function. So for logistic regression, the cost function is different. The cost function, did you see? So or it's about the possibility. So this is the cost, and still we try to minimize the cost. So your goal is still to minimize cost. And because of this, cost function is still regarding the weight W. So we can still use gradient descent. So gradient descent still applies. So if you take a derivative, you will be able to find, okay. And here the cost function, basically it is this two value because y is either 1 or 0. It is classification, is it? So that's why here you can find the cost function, okay? So over here we discuss about the logistic regression general idea. So once we understand that, so be careful, okay, logistic regression is for classification. And the odds ratio, so here it uses odds ratio. And we can take a log of the odds ratio. And it will be the net input. Okay, so then we use this sigmoid function. We call it logistic sigmoid function. So this is the decision function. And previously we already saw it. So here, like this time, this diagram gives us different about the analyze and the logic. Okay, both classification. Activation function. And the linear function is the same. The linear. Logistic regression. Activation. And this is so that's the difference in this two. Okay, and for the other one, it's the identity function. That's the difference. Okay, so this is the linear. That's what gives mooring. And what it is, it's either 1 or 0. And for this one, it's the probability. Probability to be 1 or 0. Okay, so that's the difference between these two. Careful here. So I already explained it's the probability of a particular sample belong to a class. Okay, given its feature X parameterized by the weight W. That's the definition. So here it says if the decision function is greater or equal than 0.5, then it is some class. And our goal is still to find the weights. So here, because it's considered probability, that's why here we consider all the probability together. And then we take a nature log. So this will be the cost function. Okay, the cost function for logistic regression. And basically for the cost function, then you can simplify it because y is I1 or 0. Okay, and the goal is still minimize the cost. So we can apply gradient descent. And for logistic regression, so sklearn provide this model. It has this model, so we can go ahead to see to use it. And today we will learn another concept called overfitting and underfitting. So what is overfitting? Overfitting is that the model performs well on training data, but will not perform well to testing data or prediction data. So what overfitting can be caused? It's caused by high variance. Okay, so high variance, what causes high variance? Maybe too many parameters. That makes the model too complex. So this is called overfitting. Okay, very important concept. And underfitting. Underfitting is what? Model is not complex to capture the pattern in the training data. And definitely it will perform poor unseen data also. So normally it's caused by what? Caused by high variance. Okay. Oh no, I'm sorry. It's caused by high bias. Okay, so next, what is variance? What is bias? Those two are very important concepts in machine learning. Okay, so be careful. So variance, it measures what? It measures how all of the samples spread. Okay, or its dispersion of the samples. So if the variance, so here we see the definition for the variance. So variance measures the spread, okay, of a random variable from its expected value. So that's variance. And the bias what? Bias is just the difference between the expected value and the true value of the mean value. Okay, so this is bias. So high variance can cause overfitting. High bias can cause underfitting. Be careful about these two concepts. Okay, so if variance is too high, that means it's overfitting possible. And the bias, if it's too high, that means underfitting. So a lot of time we need to do some balance, trade-off between bias and variance. So this is the concept of tune. Okay, tune the model. Normally we use what? We use regularization. Okay, so regularization is a very useful tool in machine learning to handle the high correlation, also to handle high variance. And the concept behind it is to what? Introduce bias. Because it has a high variance, so it introduces more bias. Okay. And one of the methods is called L2 regularization. L2 regularization, it's defined like this. Okay, so it's has some relationship with the weight. And we have this regularization parameter, we call it lambda. So you can tune this lambda to tune your model. Okay, so this is called regularization. So if we consider regularization, then the cost function. So you can add this regularization term to the cost function to tune the model. And in sklearn, and here be careful here. This regularization term. Okay, so that means we need to know values. And we will see. So logistic regression, you can introduce this C parameter. But the C is not a lambda. C is inverse of lambda. So if you want to add more regularization in sklearn, so that's a C. Okay, be careful. Okay. And if you want to, that regularization has less effect, then you increase that. Okay, be careful about the later on we will see about the example. Okay, so all these are regarding theoretical information. And another concept we need to know later on in our examples, we will also see this is called confusion matrix. And this is just about two classifications, confusion matrix. And the last class, we just learned one measuring performance. We use accuracy. But for machine learning, we can use more measuring performance. So confusion matrix, recall, precision, F2 value, all of those can be used to measure your machine learning model's performance. Okay, keep all of this in mind, okay? So confusion matrix is one of the measuring item for performance. So here it gives what is confusion matrix. So you have class 1 and class 2 actual value. You also have predicted value. Is it? So if your predicted is correct, so this is true positive if it's predict to class 1. If it's predicted for class 2, then it's false positive. And for class 2, you predict, so your model predicts it's class 2. But actually it's a class 1. So that's why I said it is false and negative. But if your actual sample is class 2 and you predict it, that is true positive, true negative. Is it true negative? So this is called confusion matrix. And based on confusion matrix, we can also calculate the accuracy. So we already learned it, the accuracy. So accuracy is true positive, true negative, correctly predicted. Is it over all of the samples? There are some other measuring factor. One is called recall. Recall is about what? True positive over true positive and plus false negative. This is false negative. True positive. So it's only regarding this row. Is it? So actual class 1, you predict to class 2. So if recall value is high, that means the class correctly recognized. Is it? So this is recall value. And the precision. Precision is what? Is true positive over true and false positive. So high precision indicates an example labeled as positive is indeed positive. So this is also good. But you may have some situation like you have high recall but low precision. Then that's not good. Or low recall, high precision. That's also not called. And we also have another we call F measure. So F measure, it gives us this calculation. So this is for measuring. Okay, keep that in mind. Okay, and the next, let's take a look at the examples. Okay, so first let's take a look the linear regression. Let's take a look at the linear regression. So we have some data. So this is what the data looks like. So we have value, we have, so it's quite simple. This is not classification. Because we don't have one of unit. We don't have one unit. It's all from value. So this, we are going to do linear regression. And here is the plot of the data. Plot of the data. So it's regarding population and profit. Okay. So feature is population. Feature is population. And the second column is the profit, is the value. So anyway, so here we have some basic idea about this sample distribution, is it? So next, let's see. You remember last class, we already learned for sklearn. So here we can use sklearn. The first step is to do what? Train and test split. And here, for testing data size, we take some small number, just 10% for testing data. And for linear regression, from sklearn, you can directly import linear regression model. So you create this linear regression model first. Okay, but be careful here. We first need to reshape the data. Okay, in order to train the data, you also first need to train the data because the data need to be shaped as number of samples and features for sklearn to do training. Okay, so you first need to reshape the data. And then you can feed the data. So after we do that, we feed the data. And because this is linear regression, you want to know what the slope is, what the intercept is. Is it? So you can find the slope and the intercept. And after you train, then you can predict with testing data. And you can also find the accuracy score. And you can use testing data to do the prediction. Okay. And then you can find of the mean and the standard deviation. Okay, so this example we can see, if you use sklearn, it's pretty straightforward. Is it? So you first need to split the data. After split the data, you need to do, normally you also need to do feature scaling. And then you train the model, and then you do prediction. And you also need to find out the performance. So that's generally the procedure. Okay, next, let's see the logistic regression. So this time, this is the data. What does the data look like? So this data is about student exam. So student have 2 exam score. And the last column is if the student is going to be admitted or not, based on the 2 exam scores. So we have 100 samples, okay? And here we do a very general scattered plotting. So you want to know if student admitted or not. And the first step, you do the testing and data, training data split. And then, did you see? We do feature scaling. So here we do feature scaling. So we call standard scalar. And then you need to do transform for your training data and the testing data. After that, it's straightforward. You can import the logistic regression. And you can start training the model. Okay. After the training model, you can predict with your testing data. to see how well it performs. And over here, did you see? Just discussed about the confusion matrix. So the confusion matrix contributes for performance measures. So not to precise so we will see how to use it. So here you can call confusion matrix. It's testing data. Okay. And here, did you see? You see, with the testing data, it's not too bad. So this is correctly, and this is also correct. And those are wrong ones. And for the accuracy score, it's 93%. And you can also do a classification report. You see, and the classification report, what it give you, it give you precision, recall, and the F score. Is it? If you take a look, for both classes, those two classes, the precision and the recall both are pretty high, above 90%. So that means for all of the samples, the model logistic regression here did a pretty good job. Okay, that is what this example shows. Okay, so that's regarding this example. And the next, you remember last class for that iris example, we use perceptron. Is it? So because sklearn doesn't have add line, so we just did the perceptron. Today we learn logistic. So let's see, how do we use logistic regression for that iris data set? We can skip this part because this part is a raw method for sigmoid and the cost function. Okay, we can ignore that. And the logistic regression, we skip that part. Okay. And so for logistic regression for that iris data, so here you call logistic. Be careful here about the C. What is this C? Who do you remember? To avoid overfitting. Okay, avoid overfitting. Try to make your model not overfit. Okay, then you see, you can train the model. Is it? After you train, you remember last class we said this function can do the boundary plotting, can find the linear separable line. Is it? Yeah. So here it gives the result. And here, you can also find the probability. Okay, and you plug in the finished product. Give you the probability. So based on this, which one is the best? This is 85%. The 85% that you remember that that curve is above 50%. So it is Virginia. Remember, we have these kind of flowers. So the third one has the highest probability. So it is that side. So the second sample, this one is the largest. So second sample is the first kind of flower. For the third one, it's also the first. So it gives you probability. Then you pick the largest one greater than 0.5. That means it is that high. But it's a high percentage. It's not 100%. So that's what it means. And if you recall, do you recall we discussed that the argument function is non-prime? That's why I say it's very important. So for this case, you want to know which part it is. The first sample is the third flower. The second sample is the first flower. Third one is the first flower. And you can also call predict. Predict will also tell you which class it is. Okay. And what the next parts show is it shows the regularization effects. Okay. Did you see? It does impact the regularization. Okay. This just tells us the weight. You can see the weight change a lot with the regularization. Okay, that's about this example. And here it is another example shows about polynomial regression. So for this polynomial, did you see? You can do the linear regression. Okay, you can do linear regression. And this is X value and the Y value. And when you do linear regression, you can see it's off a lot, is it? And how do we do polynomial? You can do some pre-processing. You use this polynomial feature and you specify which degree of polynomial you want it to be. Then for your feature, you transform the feature. After you transform the feature, then okay, fine. for polynomial. Okay, the last one, this is a very classical example. It's about handwritten digits. Yeah, so we call it ML-5 data set. A very, very classical. Quite interesting. I strongly recommend you read it. So here it shows. And in sklearn, you can get this data set. You just call load digits. And each digit is 8 by 8 pixel. A very rough one, 8 by 8 pixel. And here, did you see, even for this, we can use logistic regression to do training. And then do testing and prediction. And you can also get its confusion matrix. Okay, so